Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 17 Organic Chemistry 2. Today's lecture on aldehydes and ketones. We will cover nomenclature, preparing aldehydes and ketones, carbonyl compounds, aldehydes and ketones. As you can see clearly here, the carbonyl is flanked by hydrogens, while in here the carbonyl is flanked by two carbons on both sides. Nomenclature of aldehydes. Aldehydes take their name from their parent alkane chains. The E is removed from the end and is replaced by L. The aldehyde functional group is given number 1, and this number is not included in the name, but we consider it number 1 and count from there. The common name of aldehyde start with the common parent chain name and add a suffix aldehyde. Substituent positions are shown with Greek letters alpha, beta, gamma, etc. When the aldehyde CHO functional group is attached to a ring, the suffix carbaldehyde is added, and the carbon attached to that carbon will be number 1. When choosing the parent of an aldehyde, identify the longest chain that included the carbon atom of the aldehydic group. So here we have to consider that this is a long chain containing the aldehyde. So it's hexane. Take the E out, it's hexanal. On carbon number 2, we have ethyl group. So it's 2-ethyl hexanal. If this is hydrocarbons, the long chain in this case will be heptane. Okay? For this compound, the long chain containing the aldehyde is bent 4 in. So on number 4 we have methyl group. So it's 4-methyl bent 4-enal. This compound, that's cyclopentane, and you include the E, and just carbaldehyde. And if you have substituents, this is number 1. Cyclopentane carbaldehyde. Let's try to name. Here we have only 1 carbon, so that is methanal. Common name, formaldehyde. Here is 2 carbon, ethanal. That is acetaldehyde. Common name. Iobac, pentanal. Iobac. Valeraldehyde. Common name. Here we have this carbon to aldehyde alpha and beta. Beta bromo valeraldehyde. Iobac 3-bromo pentanal. 1, 2, 3, 4, 5. So this is 3-bromo pentanal. Beta bromovaleraldehyde, common name. Nomenclature of ketones. Ketones take their name from their parent again alkane chain. You take the E out and you replace it by ONE, O-N-E. The common name for ketones are simply the substituent groups listed alphabetically, then you write ketone. Some common ketones are known by their generic names, such as the fact that propanone is commonly referred to as acetone. So, propanone, well known as acetone, common name dimethyl ketone. Dimethyl ketone. Here is 1, 2, 3, 4, 5. So that's pentane 2-on. Or you can say it's methyl propyl ketone. Hexane 2-on. Common will be butyl methyl ketone. Here we have the ketone. That's 1, 2, 3, 4, 5, 6. So that's 4-bromohexane 2-on. Common name will be beta-bromobutyl methyl ketone. Some ketones have historical common names. Dimethyl ketone is always called acetone, even in IUPAC. And alkyl phenyl ketones are usually named as acyl group, followed by suffix phenone. So here is acetophenone. Here is propionol. Here is benzophenone. Give the IUPAC name and a common name for each compound, if possible. That's first compound, it's 3 carbons, number 1, 2, 3. With aldehyde functionality, it's propanal. On carbon 2, we have methoxy. So the IUPAC will be 2-methoxypropanal. Here is alpha. Common name will be alpha-methoxypropionaldehyde. Here is a carbonyl compound, that's ketone. Shortest number system to this carbonyl will be 1, 2, 3. That's 4 and this is 5. So IUPAC will be 5-hydroxyhexane 3-on. Common name will be ethyl beta hydroxypropyl ketone. For this one, we have aldehyde functionality and methoxy trans to each other. So that will be trans 2-methoxycyclohexane carbaldehyde. Trans 2-methoxycyclohexane carbaldehyde. we don't have common name. For this compound, that's bicyclic compound, we have here two chiral center, number 1 and 4. So the name will be bicyclo, that's 2, and other side 2, and here is 1, so that will be 2.2.1, and we have 7 carbon set, that will be hepta 2-on. Okay, we have to determine the configuration on 1 and 4. So we have to prioritize the 4 atom or groups atom attached to the chiral. Here we have the hydrogen in the back. We have carbon here. We have carbon here. But here is carbon followed by oxygen. Here is carbon followed by carbon, by carbon, by carbon. And this group carbon followed by carbon, by carbon. So this is 1, this is 2, and this is 3. This is anti-clockwise, so the configuration here is S. For this one, switch the molecule, flip it to have the hydrogen in the back. Again, we have this group, number 1, number 2, and here is 3, 1, 2, 3, that's clockwise, so the name will be 1s4r bicyclo 221 heptane 2-on. No common name. For this compound, this is 1, 2, 3. So the compound is cyclohexane 1,3-dione. For this one, here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's nonane 258-trione. Draw the structure of each of the following compounds. S,3,3-dibromo 4-ethyl cyclohexanone. So we start with cyclohexanone, then 1, 2, 3, 4, 5, 6 number the skeleton, 3,3-dibromo, 4-ethyl, and this should be a chiral center. So we have here hydrogen, put it in the back, and then we put the ethyl and see what's the configuration of this one. Okay, the configuration will be, this is the periodicity number 1, this is number 2, and this is number 3. So it's S. So that's the structure. For the R3-bromobutanol, first we have the butanol, then on carbon number 3, this is 1, 2, 3. So this is number 3. I put the BR up and try to see it. That now means that the hydrogen will be in the back. This is periodicity number 1. This is number 2. This is number 3. That is clockwise. Physical properties of aldehydes and ketones. Polarization of the carbonyl group creates dipole-dipole attractions between the molecules of ketones and aldehydes, resulting in higher boiling points than for hydrocarbons and ethers of similar molecular weights. Remember that we have here partially positive carbon, partially positive oxygen for carbonyl, and we have, remember that we have resonance structure from organic 1, that we have here O minus carbon plus. So there is a dipole-dipole attraction between the molecules. Let's compare. Here we have butane boiling point 0, ether 8 degrees Celsius. When you have the aldehyde, you have 49 degrees Celsius. Ketones 56 degrees Celsius. For the alcohol with the same molecular weight almost, we have 97 because of the presence of hydrogen bonding, which is stronger than dipole-dipole attraction. Formaldehyde and acetaldehyde are the most common aldehydes. Formaldehyde is gas at room temperature. Its boiling point minus 21 degrees Celsius. They handle it as formalin solution, aqueous solution of formaldehyde. But if you would like to get it dry, you can just get it from the decomposition of trioxane melting point 62 degrees Celsius, a trimer of formaldehyde, or from linear polymer called paraformaldehyde, again by heat, decomposition by heat. Acetaldehyde boiling point 20. To obtain dry, you can get it from decomposition of baraldehyde, boiling point 125, the trimer of acetaldehyde. They use it as sedative. Metaaldehyde, melting point 246 degrees Celsius, a tetramer of acetaldehyde. A bat and poison for snails and slugs. Aldehydes and ketones are soluble in water, but their solubility decreases with increase the length of the chain. So for methanol, ethanol, propanol, those aldehydes and ketones, propanone, which are of small size and are miscible with water in almost all proportions. Because of the partially negative charge on oxygen, it solvates with the delta plus of the water molecule. Delta plus of the water solvate another molecule. Preparing aldehydes and ketones. We will cover in this lecture what we have already mentioned in lecture 43 and 44, Organic Chemistry 1. Oxidation of alcohols. So primary alcohol with pyridinium chlorochromate, BCC, and methylene chloride will give aldehyde and stop. No further oxidation. Also, primary alcohol with Swarin reagent dimethyl sulfoxide, oxalyl chloride at minus 78 degrees Celsius, then treat the reaction mixture with triethylamine, will give again the aldehyde selective oxidation. No further oxidation. Primary alcohol with Curie-Chem oxidation, dimethyl sulfide with N-chlorosuccinimide as a first step, then treat the reaction mixture with triethylamine, will give again selective oxidation toward aldehyde and stop. No further oxidation. Primary alcohol with this Martin beriodinane will give again the aldehyde, no further oxidation. Reacting secondary alcohol with potassium dichromate sulfuric acid, which we call chromic acid, will give ketone. Secondary alcohol with potassium permanganate in basic medium will give again ketone. So this is oxidation of alcohols. If we react primary alcohol with chromic acid or potassium permanganate in base, that will lead to the formation of carboxylic acid. But secondary alcohol will give ketone and stop. Ozonolysis of alkene. If you have alkene with double bond, you will cut the double bond in here upon treating it with ozone as the first step. Second step, reducing agent like zinc or dimethyl sulfide. This will be an oxygen, this will be a ketone, so the disubstituted carbon will give ketone. The monosubstituted carbon give an aldehyde. Here is another example, limonene. This is will be ketone. This will be an aldehyde. This will be ketone. This one will be aldehyde, formaldehyde. So this is the formaldehyde. Here aldehyde, carbonyl, ketone. Oxidative cleavage of alkene. So if you have alkene, you treat alkene with potassium permanganate, warm and concentrated. The disubstituted carbon will be carbonyl, ketone. The monosubstituted carbon will be first aldehyde, which will be further oxidized to carboxylic acid. Here's an example. Propylidene cyclohexane will lead to the formation of cyclohexanone and propionic or propanoic acid. Hydration of alkyne. Go back to lecture 40, Organic Chemistry 1, for more detail and the mechanistic pathway. If you have terminal alkyne, you treat that with water, mercury sulfate, sulfuric acid. The addition of HOH will go Markovnikov orientation, so this carbon will have the hydrogen, and this carbon will have the OH. This in all will tautomerize to give ketone. If you have terminal alkyne, but you first hydroboration, you add H and Br2, that will be anti-Markovnikov, because the hydrogen will be on this carbon, and the Br2 will be on that one. Then you oxidize with hydrogen peroxide in basic media, will get this enol, which tautomerize to give an aldehyde. So alkyne, terminal alkyne with water, sulfuric acid, mercury sulfate will give ketone. Hydroboration, oxidation will give you an aldehyde. Oxidation of alkyne with potassium permanganate but cold in neutral media, you get the dione. If it's terminal, you get this intermediate, which further oxidize this carbon, aldehydic carbon, to carboxylic acid, and you will end up with alpha keto carboxylic acid. Alpha keto carboxylic acid. Friedel-Crafts acylation reaction For detail of this reaction, see Lecture 12, Organic Chemistry 2. So benzene with acyl chloride in presence of two equivalent or more aluminum chloride, then treat the reaction with acidified water will lead to the acyl benzene. In here we have benzene with butanol chloride, you get 1 phenyl butane 1-on. You can do Friedel-Crafts using anhydride. So benzene with ethanoic anhydride will give acetophenol. Gattermann-Koch reaction, benzene with carbon monoxide, HCl, aluminum chloride, copper 1 chloride will give you benzaldehyde. Show how you synthesize each compound from starting materials containing no more than 6 carbon atoms. This cyclopropyl phenyl ketone, retrosynthetically we can get this ketone from alcohol. This is secondary alcohol we can get from Grignard reaction of phenyl magnesium bromide with cyclopropane carbaldehyde. We can get this from the reaction of benzene, Friedel-Crafts acylation reaction. So if we start with benzene, bromination, bromine iron 3 bromide to get bromobenzene, react with magnesium in dry ether to get phenyl magnesium bromide, react that with an aldehyde, form the salt, which hydrolyze to give an alcohol, secondary alcohol. Secondary alcohol you oxidize with chromic acid to get cyclopropyl phenyl methanone, or you can say cyclopropyl phenyl ketone. We can get the compound by reacting benzene with this acyl chloride in presence of aluminum chloride, Friedel-Crafts acylation. How we can get this compound? Again, we can get this aldehyde from the alcohol, primary alcohol, and the primary alcohol we can get, since we are restricted with 6 carbon, so we can get from this Grignard reagent with ethylene oxide, or we can get this from the enol structure, and the enol can get from the terminal alkyne that will be adding the hydrogen in here and the OH in here. So Gattermann-Koch, we can do that by hydroboration oxidation. And of course we can get this from the acetylide and the bromo. This is partially positive, so connected to partially negative atom. Starting with bromomethyl cyclopentane with magnesium dry ether, you form this Grignard, this carbon which we mentioned it has negative charge, and reacting this with ethylene oxide followed by acidification, we get this alcohol. To oxidize it to aldehyde, we use reagent like BCC, pyridinium chlorochromate, or Swarin reagent to get the aldehyde. We can start with the bromo compound, react with acetylene treated with sodium hydride or sodium amide to form the salt. This nucleophile will attack to form this alkyne. Reacted hydroboration followed by oxidation to get this enol structure, which tautomerize to the target molecule. See you next lecture.